In this video, let us design OR gate and NOR gate using Nmos pass transistor. Here is a circuit schematic of an OR gate designed using Nmos pass transistor. We will learn how to write these variables for gate and as well as input terminals for both the transistor. This structure remains the same for AND, NAND, OR, NOR, XOR and as well as XNOR. We have to just change these gate and as well as input terminal values in order to design various gates. In order to do that, first we have to write the truth table of the respective gate. Here our discussion is all about OR gate. Therefore, we have to write the truth table of OR gate 0, 0, 0, 1, 1, 0 and 1, 1. A step-by-step procedure to write this truth table, convert the variables to B bar and B and similarly in the column to A bar and A are being described for two different gates AND and NAND. The link for the video is given in the description box. Here in the table, wherever you find 0 in the column B, replace with B bar. Wherever you find 1, you have to replace with D. So, generally when we write the table, it will be 0, 0, 0, 1, 1, 0 and 1, 1. So, instead of 1, we are replacing B. Instead of 0, we are replacing B bar. Similarly, in the column A, it is 0, 0. So, instead of 0, I am replacing with A bar. Next option is 0, 1. Therefore, that location is being replaced with A. 1, 0. So, instead of 0, we are mentioning it as A bar. The last choice is 1, 1. So, instead of 1, we are replacing with A. The column F holds the output of OR gate as such. Now, let us try to group the input values together. So, if we compare the first two rows, the term B bar is common. Now let us see what the output is based on the control. For both the rows, it is B bar, but the output switches from 0 to 1. So let us compare this F with A now. What is A bar? Inverted value of A. Assume if A is equal to 1, A bar should be 0. A bar, it is 0. If A is equal to 1, obviously the output is 1. So, what can we understand? Whatever is in A is as such transferred to the output. Therefore, we can assume B bar as a control signal. And what do I need in my output? Whatever is in A should be available at my output. Therefore, B bar acts as a control signal and A becomes the input signal. And whenever we have these two choices 0, 0 and 0, 1, B bar will be the control signal. So, whatever is in A will be available at the output. Therefore, we can validate 0 and 1 from this transistor. And for the next transistor, let us consider the last two rows. In the last two rows, for the column B, both are B only. Row 3 has B, row 4 also has B. What is the output? For both, it is only 1 and 1. But anyhow, let us compare with F. If it is A bar, it is 1. Again, even if it is A, it is 1. What does it mean? Whenever we have the control signal called B, the output should be automatically 1. If I want my output to be 1, what should be my input? It should be 1 because it is a pass transistor. Whatever is in input will be transferred to the output. If I expect a 1 at my output, obviously my input should be 1. Therefore, we can go to the figure. The control signal is B. I want output to be 1 whenever I have the control signal B. Therefore, I feed in 1 as my input. So, with all these variables assigned to gate and input terminal, let us write the expression. F is equal to B bar into A plus B into 1. Anything multiplied by 1 is just the variable itself. Therefore, B bar into A plus B. When we try to rewrite the expression, it is B plus B bar into A. I am taking this expression to this box. I am just using a distributive theorem where it will be b plus b bar into a plus b. 0 plus 1 or 1 plus 0 both yields only 1. Therefore, we can neglect this term and just write f is equal to a plus b, which is nothing but the expression of an OR gate. So right now, from the truth table, we try to allocate gate terminal variables and input terminal variables of two transistors, written an expression, reduced that expression, and finally derived an expression for OR gate. OR gate expression is just f is equal to input variable 1 plus input variable 2. Here it is a plus b, which are the input variables. And now, with the same idea in mind, let us try to design a NOR gate also. Again, this circuit schematic must look alike for both NOR and OR, but these input and control signal will vary. Again, it is going to be the same procedure. We have to write the truth table for NOR gate. Again, it should be 0, 0, 0, 1, 1, 0, 1, 1. In the column B, wherever you find 0, replace with B bar. Wherever you find 1, replace with B. Again, choose the column A. Wherever you find 0, replace with A bar. Wherever you find 1, replace with A. The output column F should hold the output of NOR gate, which is just opposite of your OR gate. With all these ideas, let us try to club input together as how we did for OR gate. So right now we are considering the first two rows where the B bar signal is common. Compare with the output, it is 1 and 0. There is some difference. So let us compare this F with A now. If it is A bar, the output is 1. If it is A, the output is 0. Actually, it should be on the other form. If assume A is equal to 1, but output is 0. Actually, it should be 0. The output is 1, which shows that at the output, we have inverted values of A. So, let us jump to the figure. What is a control signal? B bar. So, B bar is written here. What do I need at the output? Inverted values of A. So, in a pass transistor, whatever is in input will be transferred or passed to the output. So, what do I need at the output? Inverted values of A. Therefore, inverted value of A. A bar is the input signal. Now, consider row 3 and row 4. We have two signals, both are B. What is at the output? Both are 0. So anyhow, let us verify with A column A also. If it is A bar, 0. Again for A, 0. Whatever changes happens in A, it doesn't bother. If the control signal is B, obviously my output is going to be 0. So my control signal is B. My input is also 0, so that whenever I have the control signal B, my output is also equal to 0. By assigning these gate and input variables for both the transistors, let us write the expression. F is equal to A bar into B bar plus 0 into B. So this term gets nullified because we are multiplying with 0. It will have only A bar into B bar. When I just try to invert this expression, that is F bar. When I try to invert this expression, what happens? It is A plus B the whole bar. When I try to invert, it becomes A bar into B bar. I get this expression. So, when you just invert this term called F bar, when I just invert this term, obviously I am going to have A bar into B bar. That is what we are trying to say. Instead of just having F at the output, instead of just having F, if you have inverted F, obviously that output is going to be equal to output of a NOR gate. That is what we are trying to write here. So if you have F bar, obviously the expression could be A bar into B bar. Hope the explanation was clear. Thanks for watching the video.